Okay, so we last ended looking at how the diffuse double layer can impact the orientation of clay minerals in soil, and that's going to change the structure of the the clays at a larger scale, whether we have aggregated or dispersed materials. Okay, so what that diffuse double layer does is help structure soil, right? At the larger scale, or whole bunches of clay minerals come and stick together and orient themselves in some sort of geometric arrangement, and that leads to some sort of fabric which describes how the soil is structured, right? And also how easily it's going to be to break apart down the track. So a soil that is poorly flocculated clay minerals is going to be susceptible to being dispersed and those clay minerals going into solution and then being eroded. And the things, like I said before, that stick soils together, the cementing agents, are the clay particles themselves, right, with their associated cations in solution, and their interparticle bonding, but also, more importantly, organic compounds in the soil, so bacterial gums, fungal mycelia, and other sorts of things that help stick those particles together. And also other things like iron oxides, calcium carbonates, alumina and silica in soil. And remembering the short-range van der Waals forces that stick the clay particles together. So what that leads to is a whole bunch of different shapes of how we can describe soil structure, whether it's granular, blocky, prismatic, and so on. And we'll describe that next. So a granular structure, it resembles, if you pick up a soil and it feels like cookie crumbs, you can break the little granules apart if you really rub it hard. And this is how we describe a granular structure. This has small clumps of millions of clay particles all stuck together. And typically these crumbs have diameters of about half a centimetre in diameter. They're commonly found in the surface horizons where roots have been growing. Okay? Next we have a blocky type structure, and you can sort of see a photo of that on the right hand side and a picture of it here. So we have irregular blocks that are usually 1.5 to 5 centimetres in diameter, so they're really quite large. And they can be subangular or angular blocky, right? Don't necessarily have to be completely rounded. And we can have prismatic structures, vertical columns of soil that might be several centimetres long, maybe several centimetres across, and they're usually found below the A horizon, so a little bit further down into the soil profile. And related to that is a columnar structure. These are vertical columns, and very often they have a salty cap at the top. And that's associated with arid climate. So it's probably associated with a drying front that's propagated after, propagated down after seasonal rainfalls. And we may have a change in texture just above the top of these caps. So for example, it might be sandy on top, and so the sandy soils prevent the further migration of the salts further up, and they just accumulate at the top of that layer. We can have platy structures, thin platy structures. They're usually found in compacted soil. So in this case, they're located some 50 centimetres below the surface. And often you'll find them at the bottom of a plough pan in agricultural soils. Then we can go into single grain soil structure, so there's very little cohesion between the particles. It's just a sand, like a lot of you guys collected. It's loose, it's in loose consistency, and there's very little stuff sticking all together. And then we can have massive soil structure as well, which is almost the complete opposite. We have almost no visible structure, but you can break it up into very large clods. And these types of soils are actually quite susceptible to both tunnel erosion, because water can get down into these cracks and move off horizontally. and also they provide locations where water can accumulate and then rapidly gain velocity to start eroding. And you might come across people talking about the grade of soil structure, but really what they're talking about is how strong it is. So you can have those shapes that we talked about before, but they can either be weak, moderate, or strongly held together. So what would you guys think the grade would be for this picture? I'll let you guys make your own minds up about that. And another type of soil that is particularly important in many parts of the world is a loess. A loess occurs over large parts of Europe and China. And it's an aeolian soil, so a soil that's been blown in by the wind. And because it's wind-driven deposition of particles, they're predominantly silt-sized. And what sticks loess soils together is often capillary forces, right? Where we have these small amounts of water in the soil forming capillary bonds across soil particles. The surface tension can hold those grains of silt together. We can also get chemical reactions happening at the interface because there's water there as well, and that can lead to cementation. But often after loess have been submerged or been disturbed by agriculture or other sorts of activities, then those cementation bonds can be broken, right, because the particles have been destroyed. Or if the soil has been submerged into water. If you've got fully submerged conditions, saturated conditions, then you've got no capillary forces. Remember from our first module. Okay, so how can we assess whether those soil structures are going to be susceptible to erosion or not? And one of the simple methods to assess slaking, what's called slaking, and or dispersion. Okay, so slaking is the breakdown of those aggregates into smaller aggregates, and dispersion is actually the breaking down of those aggregates into their basically individual clay particles. And so what you end up with is something that's effectively a cloudy solution of clay particles. Let me go through all this. Get rid of so you can apply. So water and air can provide disruptive forces to soil aggregates. That can be in the form of raindrop impact. So raindrops can land on an aggregate, and the forces spread through the aggregate, and that can break apart, some of those bonds. Running water and erosion. Of course, running water can help move those particles up into suspension. Wind, tillage, livestock, freezing and thawing, expansion on wetting and drying. Okay. So for example, if we have an aggregate subjected to water and it has a shrink swell property that of the clay mineral, then that can cause the aggregates to break down. Or we can get wetting and then we get compression on the air particle, which exerts forces on the soil and breaks it apart. Alternatively, we can get the bubbles wanting to break through the aggregate, and that causes the aggregate to split in 2 or 3 or 4, right? So how do we do these tests? Well, the standard test and the most commonly used one is called the Emerson dispersion test. So what you do is you get a little petri dish and you drop your aggregate into the middle of the petri dish, and then you wait. And then you record what happens after certain periods of time. So after a certain period of time, if your aggregate looks pretty much like the aggregate you dropped in there initially, then it's probably a stable aggregate and not really susceptible, not as readily susceptible to erosion as some of the others. Over here on B, we can see a slaked aggregate. So the larger aggregate has broken down into its smaller constituent parts, right, into smaller aggregates. In picture C here, we can see a slaked aggregate that has slightly dispersed. And so the aggregate has broken down into its constituent parts, and then we're getting a cloud of suspended clay, individual clay particles in solution. And finally, the worst case scenario is a slaked and completely dispersed aggregate. So the aggregate's completely broken down. There's almost nothing remaining of the original particle that's visible, and we've just got an entirely cloudy solution. And so it's these soils here, C and D, which are really susceptible to erosion as compared to soils A and B. There's a definition here of aggregate breakdown, basically defining slaking and dispersion, whether it's by differential swelling, raindrop impact, and physicochemical dispersion, and some of the mechanisms. And I'll let you guys read through that at your own leisure. So aggregates not only break down, but they also form, right? And so there's a bunch of chemical factors that favour the flocculation or favour the development of soil structure, and they are high salt concentrations, not good for plants though, right? You have polyvalent cations, right? So cations with charges of +2 and +3 or +1. Cations that can do multiple charges really favour the formation of soil structure. And of course, low pH, because they allow some of those cations to remain in solution, okay, and be available for bonding. Whereas at higher pH, they've all precipitated out and are not available for the bonding in solution. There's chemical physical factors that favour dispersion, right? And they're the opposite, really. Low salt concentrations, sodium is a dominant cation, right? A single valency on the charge, high pH conditions, and mechanical dispersion. And of course, we can include their small-scale compressive forces, right, in destruction and aggregation. So surface tension of water on drying is a force that can stick the particles together. We can expanding and contracting plant roots, and freezing and swelling of soils can also alter the soil structure. And there's a little slide from a paper that describes basically the impact of adding organic matter, which is a sludge treatment. And you can see the organic matter content that they've measured as a function of the total amounts they've applied. And their measures of aggregate stability, right? The number of drops of water that they used to destroy 100 milligrams of soil. And so we can see with zero sludge treatment, it took 147 drops on average. As you increase the total sludge applied, you tended to increase the amount of organic matter that was incorporated into the soil, and that increased the aggregate stability, right? The number of drops that it could resist before it broke down. Right, end of lecture.